Hey, welcome back to Math with Patrick. Today is July 23rd, and we're solving problem number 204 from the Daily Epsilon calendar. And we should show why x is equal to 23 today. Looks like we have an equation with a lot of exponents. We have 2 to the power of x squared plus 1 times 16 to the power of, and it's 132 plus x, but I'd rather just write it as x plus 132. And this is equal to 4 to the power of 25x. One general strategy, which probably is going to be really useful for this problem, for exponent problems in general, is to find a common base. Here we have a base of 2, we have 16 and 4 as other bases, and all of these numbers, well, clearly 2 is, all of these numbers are powers of 2. So I'll just write 2 still as 2 to the power of x squared plus 1. But then 16 is 2 to the power of 4, I believe, right? Because we have 2, 4, 8, and then 16, and this is 4 2's all multiplied together. I'll keep the exponent the same for now, x plus 132, and then I'll call that 4 2 squared. And anytime you have these stacked exponents where you have where you're evaluating this inside exponent and then the one on the outside, it actually doesn't matter what order you do these exponents. I'll show you a quick example, like 2 to the power of 3, then to the power of 2, and we can compare that to 2 to the power of 2, then to the power of 3. Just by definition, cubing something means multiplying it to itself 3 times over, and then squaring something, this one right here, means multiplying something to itself essentially twice. And here you can see that I've produced 6 2's. We could effectively multiply this 3 and the 2, and we will get an equivalent expression of 2 to the power of 6. The same thing would have happened here, where 2 squared looks like 2 times 2, and then cubing it looks like 3, or like a triplet of all of these pairs of 2's. And either way, we still get 6 2's in the end, or 2 to the power of 6. So not only does it not matter what order you do these exponents, more importantly, is you can multiply them. So once again, this x squared plus 1 I'm not going to touch for now, but the 4 and the x plus 132 I will combine. So that's going to be 2 to the power of 4x plus, and then whatever 132 times 4 is, so that's an 8, that's a 12, and that's a 4 plus a 1 is a 5, so 528. And this is still equal to the right-hand side. I will, once again, multiply my exponents. I'll get 2 to the power of 50x. Cool. On the left-hand side right here, we have a whole bunch of 2's all being multiplied to themselves. And then we're multiplying more 2's to finally get a huge product of a whole bunch of 2's. And so I could just rewrite this with the same base. It's going to be 2 to the power of something, because we have a whole bunch of 2's being multiplied. And if I have this many 2's on the left and this many 2's in the middle, because this is on the right, then I could just add my exponents, and that'll tell me exactly how many 2's are being multiplied. X squared plus, okay, well, it is going to be plus 1 plus 4x plus 528. But let me just combine my like terms and call this a 529. That is now equal to 2 to the power of 50x. So now I have a whole bunch of 2's being multiplied over here, a whole bunch of 2's being multiplied over there. And if the equation is equal, then I have the same number of 2's being multiplied on both sides. Or in other words, my exponents are the same. So now I can just kind of remove the whole exponential part of my equation, and now I'm left with a quadratic, which to me at least, it's pretty easy to solve. I'll set it equal to 0 by subtracting a 50x from both sides. So I'm going to get minus 46x plus 529 equals 0. And now I want to use the zero product property to split my factors and get two things being multiplied. Because this is a negative and this is a positive, I know that I'm going to have two minus signs here and here. That's just because once I figure out what numbers go in these spots, when I multiply these binomials back out and expand them, the two negative numbers will produce a positive number. And then essentially the distribution here and here would produce a negative number in the middle. And partially because I already saw today's date, also partially because I know that with these calendars, there's only one solution, not multiple. I know that this number is going to be 23. Also, we could figure out that it's 23 by showing that, well, to me, it's pretty clear that the two negative 23s add to the negative 46. And then I'll real quick show that 23 squared is 529. At least it should be. 3 times 3 is 9. 3 times 2 is 6. Here's a placeholder 0 for my 20. 2 times 3 is 6. 2 times 2 is 4. And when I add these up, I do get 529. Cool. So I indeed found my factored form for this quadratic. And then now this basically shows me that once I plug in a 23 into either of these spots, I'm going to get 0 times 0, which is clearly 0. So here's my solution. And let's just see if it makes sense going back to the original problem. Well, if x is 23, then this number right here, this x squared, is 529, like we just saw. So this right here should be 530. We could plug in the 23 here. We are going to add a 23 to the 132, and that makes this exponent 155. And then this number right here is going to be whatever 25 times 23 is. Can't really do that off the top of my head, so I'm going to use a calculator. So once we figure out what those exponents are, we could then basically just run through the exact same exponent rules and figure out that these two, or the two sides of the equation, are the same. So 25 times 23 is, that was plus. 25 times 23 is 575. And so this number right here was 530. This number here is 155, and we ended up multiplying it by 4. So I want to figure out what that is real quick. So that's a 620. So this number right here turns out to be 620. And that shows us how many 2's we're multiplying here, which would have an equivalent number of 16's from above. So let me just mark that this right here is supposed to be 620. This number right here is supposed to be 530. And then once we add these together, we get 1,150. And if I double this number, it should get me the same number, 1,150. Cool, and it does. So basically, all the exponent rules check out. And ultimately, in this equation, we are multiplying way too many 2's for it to be even reasonable to think about. So all of these massive exponents to me don't really matter. I don't really care how big this number gets. I just know that I balanced the left and right hand sides of the equation. I know that x is supposed to be 23. So there's my solution. I hope you enjoyed the video, and I'll see you tomorrow. Bye.